especially the eddy diffusivity or the extra momentum flux that is arising out of turbulent fluctuations. And these two parameters are obtained at every point within the flow domain. So that is, these two parameters will be a function of x, y, z and t, and these are evaluated by their own partial differential equations, which represent the conservation of these quantities, these scalar quantities. We have already seen one such additional equation for the turbulent kinetic energy, and we look at a similar kind of derivation for the other quantity. Now, what quantities are these that would reflect properly, accurately and well enough the effect of turbulent fluctuations on the overall turbulent flux? It cannot be that everything can, any two parameters will work. It should be that they have some relevance to the turbulent processes that are taking place. And in the previous lecture we have derived the equation for K, the turbulent kinetic energy, and we have seen that a square root of the turbulent kinetic energy can be a measure of the velocity of the eddies, and these could be related, this could be analogous to the velocity of the molecules, gas molecules, which interact with each other and produce kinematic viscosity. So in the same way we wanted to, so therefore the turbulent flux is characterized by the effective turbulent viscosity, which has a velocity parameter which we have derived from the turbulent kinetic energy, and it also requires a length parameter, and it is in the length parameter that we found deficiencies in the one equation model, because we had to resort to the only length scale that we have, which is the mixing length measure, which is typically taken as a certain distance from the wall, and so that is not a very good prescription for the length scale in the general case where you may be quite far from the wall, or it may be that you have a significant influence from several walls and so on. So the idea is to derive a length scale which is independent of the geometry, and if we were to have that, then we could write an expression for the turbulent viscosity as being proportional to a constant times square root of k times the length scale, which is analogous to u times L times a constant c prime, which is characteristic of the molecular viscosity as per the kinetic theory of gases. Now, what can be the length scale here? The point that we have to keep in mind is that this is a measure of the turbulent quantities, a measure of the turbulent fluxes, and this should be therefore representing a length scale associated with the turbulent fluctuations. And this is where we also notice that we, in the derivation of the equation for K, we have come across the turbulent dissipation rate. And this turbulent dissipation rate is the rate at which the turbulent energy is getting destroyed, is being taken out of the system, and that is a very important quantity in turbulent flow. We have seen a typical spectrum in terms of the wave number k. Let us not confuse this with the turbulent kinetic energy and the energy, and we have seen that typically goes like this. This is where energy is being put into the system by this is the large eddies, and this is where you have the smallest eddies. turbulent energy is generated by large eddies as a result of destabilization of the flow in regions of large velocity gradients, and this is where one can say turbulent energy is produced, and it's characteristic of the mean flow parameters, and this energy is cascaded down the eddy sizes. As you go from here towards this, the eddy size becomes smaller and smaller, and this cascading process happens without much of dissipation of turbulence. So this is almost like a frictionless transfer of the energy that is created at the large eddy sizes, and this energy is finally dissipated here at a rate which is given by the turbulent energy dissipation rate. So this dissipation rate is happening around the smallest eddies, and the smallest eddies are so small that effectively there is no influence of the geometric parameters associated with the system. So this is a key feature of turbulence modeling, especially that the turbulent energy dissipation happens at the smallest eddies of the length scale associated with turbulence, and these are so small that these do not know whether the turbulence is created in a flow in a pipe, in a circular pipe, or in a boundary layer, or in some mixing region or anything like that. So because those scales associated with circular pipe or a boundary layer or with pressure gradient and all those things are very large compared to the small eddy scales that are happening, and this is independent of the geometry. Therefore, the length scale that appears here characterizing the turbulent viscosity is not dependent on the overall features of the flow, but it depends only purely on the turbulent quantities, and we have seen that we have here two quantities k, which is defined as half ui prime bar, sum of all the turbulent velocity fluctuations, and epsilon, which is defined as 2 nu dou u I prime by dou xk over bar. So this again is a positive quantity, square of these things. These are the parameters which depend only on the fluctuating quantities. So these are the quantities which are purely turbulence dependent, and one could therefore argue that the characteristic length of turbulent flow depends only on k and epsilon, because this is also a turbulent thing, and this is also turbulent, and this is also turbulent, and over most of the spectrum involving the wave numbers, and especially in the regions where towards higher scales, these characteristics do not depend on the geometry of this. So if one were to do like this based on dimensional arguments, because k has dimensions of meter square per second square, and epsilon has dimensions of meter square per second cube, one can say that the length here is some constant times k to the power 3 by 2 by epsilon. So this is what we can use in order to get an expression for epsilon. We can write this as epsilon equal to some constant times and this is the expression that we use for the turbulent kinetic energy equation in the one equation model. So we say that we replace this with the mixing length model, and therefore we say that this is, for example, equal to 0.4 times y, where y is normal distance, and this constant is adjusted for best fit with the data, and then we have an overall model. And we know that in this way we have a problem with the specification of the mixing length, and we make use of this very factor here to invert this relation and say that epsilon is given by okay, not it's already inverted here. We make use of this relation to substitute this into this and say that nu t is some constant times square root of k times k to the power 3 by 2 by epsilon, and therefore a constant, let us call this as c mu times k square by epsilon. So now the turbulent viscosity is given in terms of constant to be determined, and k and epsilon, which are defined as per in terms of the turbulent flow fluctuating quantities, velocity fluctuations and their derivatives. So the idea of coming up with a general model, a generic model which can account for length scale which is not dependent on one dimensional prescription, is to express turbulent viscosity in terms of two quantities k and epsilon, for which we can derive the conservation equations from the fundamental momentum equations and their manipulations. And if we do that, then we can evaluate k at every xyz t from its conservation equation like this, and we can evaluate epsilon at every xyz t using an equation yet to be developed like this. And from these things we can define nu t at xyz t as constant yet to be determined times k square by epsilon, and from these we can write ui prime uj prime, which appears in the momentum equation as nu t times du I bar by dxj plus du j bar by dxi. So in the two equation model, we develop an equation for k and then an equation for epsilon. By solving these in the usual CFD way, we can get the instantaneous and local turbulent kinetic energy and its dissipation rate. From these we get the turbulent viscosity at a local point, and using this we can evaluate the Reynolds stresses, different Reynolds stresses at every xyz t. And this equation here, which is in terms of nu t, which is given by k and epsilon, which are being evaluated using these equations, and in terms of the time average velocity gradients, is such that there won't be any new terms appearing in the time average momentum equations, and we can write time averaged equations in terms of known variables, that is u bar, v bar, w bar and p bar, and in terms of two more time averaged variables k and epsilon. We notice that although we have not put a time average here, by definition they are time average quantities. So we have 6 equations and 6 unknowns here, and by putting up all these things together we can get a description for turbulent flow, which enables us to calculate each of these quantities as a function of xyz t without having to prescribe any arbitrary values. In this modeling we still have certain constants to be determined, like c mu and other constants which we will see, and those constants are found from some experiments and some semi-theoretical arguments, but essentially people have been able to come up with a set of almost universal constants which can go into the equations which describe each of these, so that this model will be a generic model which can be used for 3-dimensional time dependent flows without having to prescribe ad hoc kind of correlations for the quantities which are involved. So let us just see how we derive these equations, and so that we have a good understanding of the model itself, and then we will discuss some of the limitations of this model and how this can be overcome, how these are overcome in higher level of models. Now, so the essence of the two equation model is to be able to derive a conservation equation for k and a conservation equation for epsilon, and so that these equations can be solved to get k and epsilon at every x, y, z, t, and we would like these equations to be in the form of the generic scalar transport equation, for which we know how to do the discretization and then converting them into a phi equal to b and then efficient solution. All that template is already fixed, and we would like equations which go into the template which describe these turbulent parameters, so that from which we can get k and epsilon and then the turbulent viscosity and then this. So how do we derive the equation for k and epsilon? We have already seen the basic idea for the derivation of k. We notice that k consists of the product of ui prime and uj prime, and therefore we have written earlier the instantaneous x momentum equation, ith momentum equation like this. Let us call this as equation 1, and then we had derived equation 2, which is the time average of equation 1, and this we can write down as dou u I bar by dou t plus dou by dou x m of u m bar u I bar plus u m prime u I prime equal to minus 1 by rho dou p bar by dou x I plus nu dou square u I bar by dou x m dou x m. And by subtracting this from this, we are able to get an equation for ui prime, which was of the form dou u I prime by dou t plus dou by dou x m of this expanded and then subtracted and all that thing, equal to minus 1 by rho dou p prime by dou x I plus nu dou square ui prime by dou x m dou x m. So there are terms that are coming here, and this is for the ith component, and what we need is ith component and ith component and summed over all the three. Therefore the key is to write an equation which is similar for uj prime. Essentially wherever you have I here, we replace it with j, and then we have an equation for this in the form of dou u j prime by dou t plus dou by dou x m of a big beast equal to minus 1 by rho dou p prime by dou x j plus nu dou square uj prime by dou x m and dou x m. And now what we do is we multiply 3 by uj prime and add to that the multiplication of every term in the fourth equation by ui prime, and then take the time average. And then we have to do lots and lots of manipulations, but this gives us equation 5, which can be written down like this. After doing these things and then doing the time averaging, we get an equation 5 which is of this form. We can see that this is the beginning of an equation for the Reynolds stresses. This dou by dou x m of um bar, that is the mean quantity here, Reynolds stresses. And here we have a term which looks really humongous, um prime ui prime uj prime. It's a simultaneous correlation, time average of the of all the three fluctuating quantities, and terms involving pressure and velocity fluctuations, but of so here we have dou by dou xi of u prime j p prime, and here we have dou by dou xj of u prime p prime correlation like this. And then we have minus ui prime um prime of here we have ui prime um prime dou u j. So this is I here and this is j, and this is the mean quantity and this is the fluctuating quantity. And similarly here we have j here and m, of course, this is the fluctuating quantity, and here we have the mean derivative. So this is the mean derivative, mean velocity derivative, and this again is the mean velocity derivative multiplying a turbulent stress component here. So these terms will appear, plus another special term which is written out separately because this is something that would not finally appear in the turbulent kinetic energy equation. Then so this is the resulting equation upon manipulations which we can get, and which, although it looks formidable, it has been derived by many a graduate student all over the world. So this has the assurance that it can be derived, but one has to be patient, and it has been put together in this form so as to give some specific meaning here. So we can see that this is of a form which is similar to the standard generic scalar transport equation, and the scalar that we are referring to here is this phi, and of course this has an index phi j. This is a stress here, and this is the advection term. This is being advected by the mean flow, that is the mean velocity here, and gradient that is coming here, so the divergence operator. And we are missing missing oh, no, this is correct. Okay, so we are missing a term which is in the generic scalar transport equation. We have an advection term and a diffusion term, and then we have a source term here, and so you have all these rest of the terms here which constitute all the unknown kind of things. These are in a way there are some terms which are known, but these do not fit into the standard diffusion term. For example, here this is another scalar phi I m, and this is another component of this particular scalar. So in that sense one could say that if there are 6 such scalars, these are known terms, and this is also known. So from that point of view, these two terms here are in a way one can say these are known or knowable when we write all these terms together. But these are triple correlations of 3 different velocity components, and these are not to be known within the context of solution of these equations, these 6 equations, along with the momentum equations and the continuity equation. Again, the simultaneous fluctuation of p and u prime again is not known. This term here is the simultaneous fluctuation of the pressure fluctuation and the velocity gradient fluctuations is not known, and this is also not known. So there are so many terms that are not known here, and these have to be given an interpretation. Now we have said in the previous lecture that and also right in the beginning that turbulence is produced in the region where you have large mean velocity gradients, and the mean velocity gradients are coming in this overall equations right here. So this is a mean velocity gradient, and this is another mean velocity gradient, and this is like a Reynolds stress term, and we have put it here in this particular way. Okay, so and we have put it in the way that minus ui prime uj prime here is nu t times dui by dxj like this, and in the specific case of one dimensional flow, this thing will become nu t du bar by dy, and that is equal to minus u prime v prime bar, and so minus u prime v prime bar is the positive quantity here. So one could say that this along with the minus is a positive quantity, and also this along with the minus is typically a positive quantity, and when this is positive and so on. So this whole thing is a positive quantity, and this is a positive quantity which is in which the mean velocity gradients are coming into picture, and this is therefore treated as a term of production of the turbulent kinetic energy. And similarly, this term here is when we put I equal to j, this becomes a positive quantity, so this becomes a negative term. So together one could call this as epsilon, and in the present form it will be epsilon ij, but once we, in order to derive from this the expression for k, we have to put I equal to 1 and j equal to 1 here, and then write an equation for the u prime square, and then you put I equal to 2 and j equal to 2 here, and then do the corresponding thing. So essentially when we put I equal to j equal to 1, 2 and 3, we get the 3 normal stresses, and then we add them together to get the overall k equation. So when you essentially, as far as the turbulent kinetic energy equation is concerned, I is equal to j. So in that sense this will go away, and then we have an epsilon here, and at that point this is a positive quantity. So this is the rate of dissipation of turbulent kinetic energy. So this is something like a sink term, So this is a source term and this is a sink term for this. This term is such that although this is not known, once you put I equal to j, this thing goes to 0 because this becomes dou ui prime by dou x prime, dou x and dou xi, and that becomes equal to 0 because our instantaneous continuity equation is dou x I by dou x, dou ui by dou x I equal to 0. The time average form of the continuity equation is dou u I bar by dou x I equal to 0. So if you subtract this from this, you get dou by dou x I of ui minus ui bar equal to 0, and this is nothing but dou u I prime by dou x I is equal to 0. So that means that when you put I equal to j here in order to get the normal stresses, then this term is identically 0, this term is identically 0, so this won't come into picture. So that's why we want to decompose this into this form. So of all the terms that are appearing here, these two terms together constitute the production term as a source term, positive source term, and this term here constitutes a sink term which is trying to reduce the amount of turbulent kinetic energy, and this is the term. These two terms are essentially not known very well, and what people have tried to show is that there is that this, although this term is being neglected in the case of, is cancelling out in the case of k term, this is very important in the relative magnitude of the various normal stresses. So in that sense it's a very important term, and because of the connotation between this u prime m fluctuation and dou xm gradient that is coming here in this, and if one were to treat this as a scalar that we are dealing with, the scalar is the time average quantity of this, whereas this is the instantaneous quantity of that kind of thing. So it's not exact, but if one were to say that this is phi here and this is dou by dou xm of u prime m O bar, then it becomes very similar to this, and this represents the turbulent diffusion of x momentum. So by the same token, this can be considered as turbulent diffusion of this quantity, which is the k-like quantity here. So this term is not very easy to deal with. So together these terms are brought under the umbrella of turbulent diffusion of k. So this equation for the Reynolds stress, when we contract the indices, that is when you make I equal to j here and then write an equation for dou by dou t of half ui prime, which is nothing but k here, finally takes a form like this. This is the turbulent diffusion, and we have turbulent diffusion of momentum, and this can be considered as an equivalent of the Prandtl number for k. So Prandtl number is the ratio of momentum diffusivity to thermal diffusivity. Okay. So and that comes into picture when we are looking at temperature gradient and the corresponding thermal diffusivity. Here we are looking at diffusion of k. Okay, so the sigma k can be called as the equivalent of Prandtl number or the Schmidt number for k, and this is essentially by the turbulent mechanism. So we can put it like this. So this is the overall effective diffusivity of K, and then we have the production term. When you put I equal to J here, then this becomes 2 times this, okay, 2 times ui prime um prime here, and we have to divide by half throughout. So ultimately we can get, and this quantity is expressed using this expression here, so that once you put this into here and then you do this, you get the overall production term nu T dou u I bar by dou xj plus dou u we are using m here throughout, so we can use m without any loss of generality. So that is the production term which takes account of this, and this term is 0, and then we have minus epsilon. So this is the overall equation for K, which is derived from some kind of hand waving argument with respect to the diffusion term, and especially with the triple correlation, but otherwise one can derive this exactly. And in the process we have introduced only one constant, sigma K, and we have made use of the Boussinesq type of hypothesis to represent these things as nu T times du I bar by dxj and all this when we are dealing with the production term. So in this way we can derive the equation for K, and the derivation of epsilon is also similar. In the case of K equation, we wrote an equation for ui prime, and then we wrote an equation for uj prime, and then we multiplied by uj prime here and then ui prime here, and then added them and then took time average to get an equation for this, and then we contracted the indices. Epsilon here has dou u I prime by dou xk, dou u I prime by dou xk time average. So once we do this, we have to take dou by dou xk, we need to take the divergence of this, and that will give us an equation for dou u I prime by dou xk, and then we have to take again the divergence of this whole equation to get dou u j prime by dou xk, and then we need to multiply this by this and this by this, and then add them together and then take the time average, and then we get a horrendous expression involving many more correlations and many more unknowns, plus some terms which we can readily identify. Okay, so just as in this equation, in this is the exact equation without any assumptions here. This is derived wholly from the Navier-Stokes equations and the continuity equation, and in this we can identify this term and this term readily, and we can identify some elements of these terms, but there are number of terms which are not identified. The number of terms which are not identified for the epsilon equation is much more, and all of them are swept under these generic terms. Okay, these will be exact. You have a diffusion. Okay, so one can say this is turbulent diffusion of K, production of K, and this is the dissipation of K. So a very analogous relation is finally derived from the mess that is that comes out of all these operations here. and then the final equation will be of this form. Again a diffusion term which is very loosely written and analogously written as nu t by epsilon sigma epsilon plus a production of epsilon which is essentially this term multiplied by epsilon by k. So C1 epsilon by k times this term and this term is also multiplied by another constant C2 epsilon by k multiplied with that will give us epsilon square by k. So this is the modeled equation for epsilon, and that is the epsilon equation that we are talking about. So this is only loosely and roughly derived from the exact Navier-Stokes equations with a lot of approximations and simplifications. And when you look at the equations, the additional equations that we have to solve, we see that these are of the standard form, generic scalar transport form, with an accumulation term, an advection term, a diffusion term, and production plus source and sink terms put together. The only difficulty from a mathematical point of view is some of these terms are nonlinear, and this term is a function of epsilon, this term is also a function of epsilon, and in this is an unknown, so there is coupling introduced between this and this, and there is coupling introduced between this and this together through the k term which is appearing here, and there is coupling introduced between these two and the momentum equations in the form of the expression for ui prime uj prime here, which is expressed in this way, where nu t itself is expressed in the form k and epsilon. So we have the overall set of equations, the 6 equations that we have for u bar, v bar, w bar, p bar, k and epsilon are very strongly coupled among each other through this algebraic expression and through these expressions for k and epsilon, which not only are intercoupled through the dissipation rate and then the production rate, but also with the mean velocity gradients which are coming in the production term. So the source term linearization and the treatment of the source term is very important, especially when we are talking about the turbulence model. But other than that, the equations look very similar to what we have, and the things that are yet to be determined are the constants sigma k, sigma epsilon, C1 epsilon, C2 epsilon, and the constant which is coming here, we have written it as C mu, which is appearing in mu t being equal to C mu k square by epsilon. These constants are determined partly from some estimates of what is expected. These are effectively Prandtl number for diffusivity of k and epsilon, and in real case when we talk about fluids, the Prandtl number of a fluid can be very different from 1. For example, the Prandtl number for gases typically is of the order of 0.7, but for water it is of the order of 7, and for some organic liquids it can be very large, going into thousands, and for liquid metals Prandtl number is very low of the order of 0.01. So there can be quite a lot of variation for real fluids. Similarly, the diffusivity or the Schmidt number, which represents the ratio of the kinematic viscosity and the diffusivity, the mass diffusivity. So that can also vary over a very wide range when you look at the typical fluids, and in those cases the mechanism is by molecular interaction. But in this case the diffusion that is coming here and the diffusivity that is causing the diffusion of K and epsilon is essentially by the same mechanism which is also causing the turbulent diffusion of momentum, and that is arising out of mixing of different fluid molecules by the fact that we have turbulent fluctuations and by the fact that we have this eddying structure. So the rate of this mixing and the rate of this effective flux that is generated is determined essentially by the intensity of turbulence which is causing the eddies to be present, and also the size range of eddies that are present. So in that sense the mixing of K and epsilon, these are different scalar quantities, is not governed by the intrinsic property of the K and epsilon, but it is governed by the rate of mixing, and it is the size of the turbulence that the size of the eddies that are present. So whether we talk about the momentum diffusivity, the turbulent momentum diffusivity, or the turbulent viscosity, or the turbulent Prandtl number, or the turbulent Prandtl number for K, that is the sigma K and sigma epsilon, all these are dependent on the same quantity. Therefore the ratios of the turbulent momentum diffusivity to turbulent K diffusivity, which is what is represented by the sigma K, this should be of the order of 1, and this is also of the order of 1, and the precise values of these are adjusted by comparing the overall result for velocity profiles and turbulence levels in experiments, but these two are expected to be of the order of 1. Now this quantity here is determined under conditions where this the K equation, the K evolution and epsilon evolution are determined wholly by the source terms. Okay. For example, when you are looking at cases very close to the wall where under steady conditions where um is very close to 0, okay, and the diffusion term can be neglected, and it is the rate of production of K and the rate of local dissipation of epsilon, these two factors dominate. So under those conditions one can show that C mu is minus u prime v prime square bar by K whole square, and measurements show that very close to the wall, at which point there is equilibrium between the rate of production of K and rate of dissipation. Under those conditions measurements show that this ratio is of the order of 0.3, and so if you were to plot along the radial distance r by r and this quantity minus u prime v prime by K, we note that K is also a turbulence quantity. So this we find typically it is like this around 0.3, and close to the wall it goes down like this. Over a large portion of this r by r equal to 0 and 1. So over a large portion this has a value of 0.3. So based on that you put this here, you get C mu equal to 0.09. Now under the conditions of decay of grid generated turbulence, that is, you have a grid, you have a mesh, and you have flow going over it, and you have essentially uniform flow going over it without any significant velocity gradient. This the fact that it is flowing over these wires will produce some velocity gradients and turbulence and some fluctuations of k and epsilon, and as you go past this grid there is no more generation of turbulence, because at this point du bar by dx m is going to be 0 because there is no mean velocity gradient. So this term will be 0. So and this term will be 0 because there is no okay, this is 0, this term is there, and so this term is usually negligible. So you have a certain rate of decay of k with respect to distance, and based on that, and we can get this value here, and so based on these considerations we can fix the overall values for the constants. These vary from person to person. C mu is 0.09, C1 epsilon is 1.44, C2 epsilon is 1.92, sigma k is 1.0, and sigma epsilon is 1.3. So these are the typical values, and one can see that these two are of the order of 1 here, and these are fixed by the grid turbulence and other measurements, and this is based on the velocity measurements close to the wall here. So once these values are specified, then in this equation we have only epsilon, which is the parameter of importance here, and this equation determines the value of epsilon at every x, y, z, t, and similarly in this equation this value is known and everything else is in terms of known variables, and therefore this can be used to calculate k. So in the two equation model, of which this is one particular form, in the two equation model we are solving two equations, the turbulent kinetic energy conservation equation, the conservation equation for the rate of dissipation of turbulent kinetic energy, it is a big quantity, and these two equations are solved for the instantaneous local values of k and epsilon, and from these things we evaluate the instantaneous local value of the turbulent viscosity using the constant of 0.09 and k square by epsilon, and using this instantaneous local value of the turbulent viscosity we evaluate the Reynolds stress component in terms of the Booth-Nesk hypothesis, where you have the mean velocity gradients that are coming here. So this value, in each of the momentum equations there will be gradients, appropriate gradients of 3 of these fluxes, and these fluxes are evaluated and these come into as source terms in the source terms or effective diffusion term in the momentum equation. Therefore in the momentum equation we no longer have to write this ui prime uj prime, we need to write only this, but in order to evaluate this term we need to know this, and in order to evaluate this we need to know these two, and these two are obtained only from these equations. So when we talk about a turbulent energy turbulent flow calculation using the two equation model, we have the continuity equation which will be put in the form of a A1 P prime equal to B1 in its discretized form to give the pressure fluctuation and pressure correction, and from this we get the mean value of pressure. Please note that this is not pressure fluctuation, this is the pressure correction, and then we have the discretization of the time averaged x momentum equation will give us A2 u bar equal to B2, and the discretization of the time averaged form of the y equation will give us A3 v bar equal to B3, and similarly the time averaged z momentum equation will give us A4 w bar equal to B4, and the discretization of the k equation right here will give us A5 k equal to B5, and the discretization of the epsilon equation will give us A6 epsilon equal to B6. So we have a big loop in which we evaluate this, and then 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 we can evaluate this, we get nu t, and using nu t and available estimates we can evaluate the ui time and uj time terms, which will feed into these things, and then once we update all these things along with the updates which go into this, we come back and do one more iteration. So we can do each of these things sequentially, that is one after the other, and update the values frequently with an under relaxation and get an overall evaluation of the time average velocity components and the pressure and the local time average quantities representing turbulence k and epsilon, from which we can determine the diffusivities and so on. So this is how a two equation model of turbulence works, and what we notice is that these conservation equations do not require specification of the turbulence quantity of the mixing length or turbulent viscosity or anything like that. These are self-consistent contained equations, and there is no more need to say anything other than the fluid properties, the flow domain, and these constants. The only thing that remains is the boundary condition. There are certain boundary conditions very close to the wall, specifically for k and epsilon, and we have to give some special treatment at the wall, and that forms the subject of a large variety of turbulence models, the near wall turbulence thing. We do not have that much time in this course to deal with all the turbulence modeling approaches, but we need to do something close to the wall. Near wall treatment of turbulence, I would refer you to standard books on turbulence modeling and advanced fluid mechanics, but one approach, one simplistic approach is to use some kind of wall functions which roughly capture the variation of k and epsilon and the velocities very close to the wall, and they give rise to algebraic prescriptions for what the UVW and k and epsilon would be close to the wall, and that way we can overcome the special effects associated with near the wall. There are much more advanced models like that. So along with these wall functions or wall prescriptions for this, we have a complete description of all the parameters that describe fairly adequately and in a fairly general way a turbulent flow, and one would have to solve these extra equations in order to come up with the calculation for turbulent flows. So in the next lecture we will see how we can extend this when we have for example the calculation of non-isothermal flows, that is what we can do for the energy equation and also for the typical scalar transport equation, where we are looking at mass transfer or flows with chemical reactions and so on. With that, we will be able to say that we would now have the equations which describe turbulent reacting non-isothermal flows, and all of these are put together in the standard form, and they can be readily appended to the methodology that we have already developed for a typical CFD calculation.